is to show more in the program and provide a little bit of background information, sort of what's going on behind the curtain. So my first slide here, which I hope you can see, I'll have the chat window on. So I will sort of glance at it off and on and let me know if something isn't working. So, the ODYSSEY is a bona fide computational chemistry program, which really sets it apart from what's usually used in education. There are two computational engines in the program, one for quantum chemistry and one for molecular dynamics simulations. And I want to talk a little bit about what's going on there and show a few more slides later. I have a total of 8 slides. First though, I will go back to the program by selecting stop the share screen and switch to ODYSSEY share. And I hope that you can now see the ODYSSEY start page. So Dr. Shyam has already shown a bunch of examples. So I will basically just reiterate what he already did. Build a simple water molecule. The 4 billion block is always my thing. So here's the water molecule. And he had shown you how to generate the polarity map for this molecule. I want to quickly look at the 2 other options in the menu. The first option is high density. So this is an isosurface sketching out the shape of the molecule, the electron cloud, at a higher density value, so close to the nuclei. And then there is low density, that's further out. And then polarity map is simply superimposes on that a color scheme, which that picture you saw before, where you can get a really intuitive visualization of the charge distribution in the molecule. So I want quickly here to it's in the menu. It's labeled low density and high density. What are actually the numbers associated with that? For that, I will go to the start page of the program. I go to labs, and I will go to I have the complete list, and I will go to electron sharing and molecules. So this is one of the content pages in the program. There are hundreds of pages like that, where here there's a pre-calculated for water molecule different isosurfaces of the electron density. And here you see numbers. How much of the density is actually enclosed by the isosurface. So if I hear for medium low, it's 90%. So 10% are still outside of that. Very low, 99.9%. At that, if you go that far out, water becomes in fact, an almost spherical molecule. If I go to 70% only included, now I get this shape. If I go to 30%, there's only density on the oxygen. There's nothing left here for the hydrogens. This is what you would see in an X-ray diffraction experiment, where you can only see the heavy atoms. You wouldn't see the hydrogens. So here's these models here were pre-calculated with Spartan, the other program, and they are automatically loaded into ODYSSEY, and you can just pull them up. So these models were generated with good quantum chemistry, density functional theory, I don't want to go into details, sort of a demanding model. If I do it on the fly, this here was, if I change quickly, if I run one time, or if I run time steps, the surface goes away, because we don't solve the time-dependent Schrödinger equation. We can only do the time-independent one. If I regenerate this here, so this here took 2 seconds or so. This is cheap quantum chemistry. For the experts of you, it's Hartree-Fock, so it does not include correlation. Hartree-Fock 631G star, so which is sort of a cheap quantum chemistry, but it's allows you to do it sort of interactively. And the limit is 30 atoms. So in the program, it's 30, in Spartan you don't have that limit, but here in Odyssey it's up to 30 atoms. The idea is simply, to keep it interactive, so not to have to wait. I mean, so within the the attention span of a student who would use this program. Now, if I want to compare this picture here, for example, with hydrogen peroxide, how can I do this? I can here, chemistry is so much about comparing things, not things absolute, what they are like, but how do things differ? I can here select an icon. Okay, so we are getting unlimited minutes. So I'm getting a dialog. I select the icon here for compare side by side. Then there's a dialog here where I can search for more systems. I will type in here hydrogen peroxide molecule, select this. Now here on the left side is my water molecule that I built from scratch. It's one mouse click. And here on the right side is my hydrogen peroxide. Now here is, I mean, this here is just an arbitrary example to show you the functionality. So you can do your comparison. You could do primary alcohols and secondary alcohols or whatever, ammonia and water and so on. Different, for example, compare polarity in terms of the polarity map or in terms of the dipole arrow. Here I'm showing the dipole arrow for this molecule. I'm showing the dipole arrow for the other molecule. Dipole arrow on the left side. There's always you see there's a red screen around which side of the two models is active. But now I chose the right side, and I go to here, dipole arrow. So here are this here is a smaller number. I can quantify that if I go to properties, add property, lower left corner, electrostatics, dipole moment quantum theory. So here it's 2.14 to buy for this one. Here for water it's 2.46. This is the true dipole moment of water is in the gas phase is about 1.8 to buy. Comes out as 2.46 because we are doing cheap quantum chemistry. So you can't get it all possible ways. You won't get perfect results, if you do things cheaply. So, but the trend will always come out right. So I will again here hide my hydrogen peroxide. Go back and quickly here run a quick simulation here, and put the polarity map back. And now I'll turn off the dipole arrow and add another water molecule. Dr. Shyam had already done that with the glucose where he added waters. So, oops. Here I go to add atoms, add another molecule, and do the polarity map. You can see now I can do this. There's the progress bar you see at the bottom of the screen. I can here, if I move one of the two molecules, I can do this by holding down the control key. You can see how it updates sort of on the fly. I mean, there's a 2-second or so delay because, I mean, we are solving the Schrödinger equation every time I'm moving, one of the two molecules. So, I mean, it's sort of quite amazing what you can do there. So, but here, visualize again the hydrogen bonds as here you see the dotted line. Here's the here I'm breaking the hydrogen bond. And here, I'm forming. So if I add more molecules, so I can.
मुझे तो वो कह रहा था कि.
And I run the simulation. I should have minimized that first. I'll do this again. I'll do a bunch of molecules. Minimize. Should always be the first step. And if I now run the simulation and have the hydrogen bonds here, I can slow the motion down. And I have, you see here, how they spontaneously stay together, because of hydrogen bonding. If I stop the simulation here, another visualization feature, if I select lone pairs below hydrogen bonds, you get a cartoon representation of the lone pair positions in the molecules. This is sort of, that was something from as a serious computational chemist, you cringe a little bit if you look at the picture, but that's, I'm saying it's a cartoon. It's not, this is not, doesn't mean that, lone pairs are, they're two little spheres, they're floating around in space. It's something to indicate, where the lone pair positions are in the molecule. And we included this sort of because of great demand by instructors. So even though it's a very, very cartoonish representation. I'll turn this back off. And now to go from a water cluster to liquid water, I'll do this, you can do this sort of similar how Dr. Shyam built already a model of air. I go to simulation cell. I go to liquid and make it a density of 1 gram per cubic centimeters. And instead of 7 water molecules, I make 50 molecules and click apply. I'm generating here on the fly now a simulation box where I can hide this. And this is in fact a bona fide model of water. If I switch to the space filling style, you can see here there are cavities in there and stuff, but it's basically the molecules are, compact, close, sort of irregularly, in a disordered way, packed inside the box. If I go back here to ball and spoke, here's a useful feature. Whenever I have a system like that, there's lots of detail there. How can I focus on just part of the system? I pick with the right button of my mouse, I pick just one oxygen atom, and I select a set clipping center. And now I'm only showing inside of. And here you can see I can change the radius of the clipping sphere. So here I'm now, it's the entire system. And here I'm now just showing the local environment. And I can even run the simulation while this is. So you see here the, the typical, fourfold coordination that we in perfect in ice, but, this retained even in water for that is associated with all the unique properties that water has. So your style clipping, I can turn off. Here's a complete box clipping on. So let me show you. So this was a little bit more complex simulation. For that, I'll go to here to the miscellaneous section. Here, the toolbar, and I go to blood sugar regulation, the medicine section of the program. So here's the glucose molecule. Dr. Shyam had built it from scratch. So here's now glucose literally now in the simulation box with, I don't know, 100 or 150 molecules surrounding it. And glucose dissolves, in huge amounts in water because it seamlessly fits into the hydrogen bond network of the solvent. So this here's the little topic here is blood sugar regulation. So now insulin, the hormone that is, controls that. Here we, see a molecular dynamic simulation of insulin, the model that you can basically get from the protein data bank, PDB. Any PDB model you can pull in as a PDB file and it will show effortlessly. Some of them we simply included with the program. And what we then did is, simply clean them up. Most of the stuff in PDB actually has gunk in it, and counter ions and water and all kinds of, and sometimes acetic acid and stuff like that. We cleaned that up, but otherwise, it's sort of a straight PDB model. You see here the alpha helical shape of the molecule, and with the disulfur bonds and so on. I will now for a minute go to stop this share and share again my PowerPoint. Share and go to the next slide. So how molecular dynamics, it's some, unlike quantum chemistry, which is a real art form, molecular dynamics is conceptually very, very simple. How it's done, it's basically, just solving Newton's equation of motion from hundreds of years ago. We have a snapshot of the system with their positions. We have an energy function, this function of the positions of all the atoms in the system. The gradient of the energy gives us the force. From the force, we then get an acceleration. That means velocity over time. And we can use this in order to find a new position. And then we just have to iterate that. Pretty straightforward. The typical step size for this is 1 femtoseconds. So you can run, when you're watching the simulation, you typically will see things happening on the order of, 100 steps per second, wall clock time or so. With the step size of 1 femtosecond means you can really reach a time scale of picoseconds. Dr. Shyam already said that, or up to nanoseconds. If you keep the system simple enough and run long enough, nanoseconds are also achievable. But you can't go further. You can simulate chemistry that genuinely requires microseconds or seconds or something like that. It won't happen. I mean, everything's on the molecular scale. The limiting factor is the high frequency vibrations of the molecules. Many people are unaware of the fact that this is actually a very, very old technique. It's just sort of unknown in the world of teaching, which is a shame because it has been around now for over 50 years. First simulations using continuous potentials goes back all the way to 1964, which was Anis Rahman from India, who is unfortunately no longer around. The first sort of correct, in quotes, simulation of water already in 1971. It was a long time ago. First million particle simulation, 1987, billion particles in material science, over 20 years ago. Along those lines here, if you now, given what we are currently dealing with, here is this is here, the absolute frontier, the coronavirus simulation, which was just carried out March 12th and 13th for 2 days of supercomputer time on one of the two supercomputers in Austin, at the University of Texas in Austin. So this is apparently an all-atom model of the virus envelope, not the complete thing. That would be even more, even much bigger. But already this 200 million atoms, they have simulated this. Apparently, they got to a nanosecond time scale, and this was all run on 250,000 cores. No, it may sound like overhyping, but it's true that the program ODYSSEY is conceptually exactly the same that was used to do these simulations. Everything is much bigger. It's astronomical compared to what ODYSSEY can do. While I'm doing this presentation, I'm using a Lenovo laptop with 2 cores. So I'm off by a factor of 125,000 from what was used to simulate the coronavirus there. And I don't have enough memory, to represent 200 million atoms. But otherwise, actually, the complexity of the models is about the same as it's used by ODYSSEY. The devil is in the detail as usual, but it's very, very similar. Here, the headline, coronavirus massive simulations completed. You have to take that with a grain of salt. I mean, yes, the simulation was carried out, an initial simulation for 2 days. The research, of course, is not completed at all. It was just initiated. So, but, it's a little bragging there. So that's by using a tool, dynamic science-based molecular visualization tool in education, students get to use a tool that is very similar to an actual research tool. So that's different from, so many other things which are sort of rather toy-like that is used in education. This is the real, it's all packaged to be easy to use, and we keep all the technical details behind the curtain. but it really mirrors the actual research tool closely. So, which is you know, a very motivating thing for factor for many students. I'll close my PowerPoint and go back to the program. Stop share and share screen, go back to ODYSSEY and do a share, and hopefully I'm back here by my at my simulation, and want to show you in the second half of my 40 minutes a few other things in the program. I'll go to the you see, by the way, here you can have all these pages. It's like a book where you can have multiple pages open at the same time. I mean, here are eventually you'll run out of memory, but you can you don't need to close, you know, the models that you have open. So I go back to the home page, and I will go to labs, and here go to examining reaction mechanisms. So this here's an example now, which is not a molecular dynamics simulation, but an animation, but based on high-level quantum chemistry calculations with using density functional theory and so on, for the hydrolysis of the fluorine equivalent of phosgene, COF2, carbonyl difluoride. So if I scroll here through, and all this was calculated with Spartan. So you can, if you have Spartan, you can, in principle, you can calculate the sequence. It's going to be, there's really a learning curve now. See, you have to know the program very well to do this, because it's you have to define exactly, you know, the right reaction coordinate and so on. But if you do that, so it's generated with Spartan. Spartan was the authoring tool for it. And if I here, yeah, I can now show the electron density as the bonds here break and new bonds form. And I go here from the reactants to the products. You always have the option here, different styles for the surface, for the iso surfaces. Here's the mesh style, or here's a solid style. I can also here look actually at the energetics of this process, and you'll see, you know, how complex that is, which is typical for kinetics. Kinetics is almost always very complex. It's very hard to come up with simple examples in kinetics. I select the plot option and put here XY plot, and select the reaction coordinate on the x-axis and relative energy in kilojoules per mole on the y-axis. And let's do this. Let's do a smooth fit. Finish. It's sort of similar as you have it in a spreadsheet in Microsoft Excel or something like that. So here's on the left side, you see how. So I scroll through there through the model. You may see probably all delayed on because of it has to go over the network, but I'm here. There are no fewer than 4 transition states in this, and 3 intermediates in this so superficially so simple, such a simple reaction. I mean, you can now analyze that in terms of, you know, is it exothermic, endothermic, you know, what are the activation barriers for the various steps, and so on. Another kinetics example is, if I go back here, reactive collisions between molecules. It's the previous unit, you know, teaching unit in the labs page of the program. So here's here we have done, this is actually no molecular dynamics, but what we have done is parameterize the quantum mechanics to a classical model, so that you can get away with by doing it classically, but simply by its you know, very complex representation of the quantum chemical energy surfaces. So here I have an N2 and an NO2, nitrogen dioxide, and a fluorine molecule. So they just bounced off because the conditions were not fulfilled for a reaction. So because now the idea is actually in a student lab, you know, have students discover what do I need to do in order to make them react. I will here simply now go immediately go to the correct answer. So I jump ahead, you know, what in the lab really should take half an hour. And here I got now my reactive event. So I can also now, if I can control the amount of energy that goes into the system. If I will now put it back into this here is the perfect, you know, this is the orientation that would actually lead to a reaction. But I will go here to energy, total energy molar, and I will lower this from 67 kilojoules per mole to 10 kilojoules per mole. And I will now, if I run the simulation, they will already fly a little bit more slowly because there's less kinetic energy. And now, even though this just earlier, you know, when I was above the activation barrier, this led to a reaction. Now I'm below the activation barrier, and even though the steric conditions were fulfilled, I don't get a reaction. So that's an example of kinetics. So can you do other chemical reactions with the program? No, not really, because chemical reactions really you would have to solve the time-dependent Schrödinger equation. You can't get away with less. So it's like some. In this one particular case, we have done all that, but for you know, open-ended, you know, you defined your own reactants, you know, and just let it go, and bonds will break and new bonds will form. That's something left for the work for the age of quantum computers. That maybe we will still see this in our lifetimes. We will see, but it's not going to happen even with the supercomputer in Texas that's now simulating the coronavirus wouldn't be fast enough to do that. I'll go to show you another example here for where the formation of compounds where you do not have to do fancy quantum mechanics because it's simply all Coulombic interactions. The bonding in ionic compounds. So this here is a unit on bonding in basically sodium chloride. So there is if I start the simulation, I should check on the chat quickly that I hope I lost the chat window dialog, so I hope everything is fine. So because I'm okay. So here we have, it's basically a simulation like a gas of two types of spheres, positive, which are sort of like a model of argon, but with two types of argon that, you know, it's just some of them are blue and some of them are yellow. Now, if I put charges onto these, if I go to the charge dialog here and put positive charges on both of them and run the simulation. So, you know, it's simple electrostatics at work. Now, if I put only the charges on one of them, so you see here, you can, have students predict what the behavior would be. You can play all kinds of pedagogical games with that. Now, if I go here now, of course, the eventual goal is +1, -1, and I do OK, and run the simulation. And you see here the spontaneous generation of the structure. If I stop that, and compare this with sodium chloride. You see here, this is the perfect model, and here I've generated I'm generating the same model sort of on the fly. Here are this here is for sodium chloride, cesium chloride, and ammonium chloride, sort of basic structures. Here are now, for comparison, actual structures. These come from various public databases of solids, where which just are more complicated complicated applications of the same theme, that gives rise to the sodium chloride structure. I'll do 2 more examples and then show the last 2 slides, and then I will have used up my 40 minutes, because even though we don't seem to have the strict time limit, we won't get kicked out necessarily. I don't want to steal too much of your time. So I'll go back to the homepage and go to the stock room. Gives me a chance to go to the stock room once. So in the stock room, there are models of all the elements, most of the allotropes, and so on. I will go to the fluorine page here. So fluorine molecule, fluorine gas. So I'm pulling here fluorine from the stock room, and if I run the simulation, so obviously this is not something you would use fluorine in a teaching lab. No way you would do that. So, and if I can here, first of all, here a few more, I can highlight motion in the gas phase by here putting trails on molecules. You see, I'm following the motion of this one. They just bounced off the wall. I can show collisions the molecules with the walls. I'll turn that back off. And I can do, should turn collisions, none, okay. And I can, our cat here is walking around on my desk. It's distracting me. If I do, I can now measure a simple example here of generating other types of plots, also a type of visualization, not molecular visualization, but traditional data visualization. If I do, I can measure I can change the volume of the system, that will affect the pressure, and I can do this with the plot. If I put XY plot and the volume on the x-axis and the pressure on the y-axis, and do a smooth fit here, finish, and get a data point. And so here I'm doing something very quickly randomly. And you see actually, it doesn't all come out perfectly because we are doing a computer experiment in real time where there are error bars, and it doesn't, eventually will come out textbook-like, but there's not the instant verification of in so many in these toy apps that you have for processes like that, where everything comes out perfectly. This is a real simulation, of the real physical system, and so you get dirty in quotes data, which nevertheless, if I don't change here the volume here to 1 over x or 1 over p versus the volume. No, I mean here I'm already starting to get the linear dependence and so on. Okay, last example, I will build something biological. So Dr. Shyam already did a peptide. I will build something here, a piece of DNA, Watson-Crick DNA, by going to the nucleotide builder. Just as he just shows a random sequence of amino acids, I will choose a random sequence of base pairs. One shouldn't make it more than sort of 30 base pairs. It's basically, the rule of thumb is no more than 1,000 atoms total, because then everything gets awfully slow. So 1,000 is a reasonable. 1,000 is about the pain threshold. So if I click on the background, here's my model, and it's hung up. Oops. And I can do the same game that here with the ribbons and here by secondary structure. So now I can here, if I change the style here to the tube style, I can show the hydrogen bonds connecting the two strands. And now the important pointer for the biological function of DNA, in order to for transcription and translation to be able to work, I have to get to the to the individual strands, and for replication they have to be able to come apart. And in fact, these are conceptually two molecules that we have on the screen. And I can here, I hold down the control key while I'm doing this. I can break the hydrogen bonds here and and reform the molecule. And if I then start the simulation, this is now a piece of DNA in the gas phase. I could put water around it, but I will very quickly, I will exceed my, the 1,000 atom limit that I sort of suggested one should stick by. If you have immerse that in water, you get huge moles immediately, and it's no longer practical, even though it's perfectly doable in principle. Okay, I'll leave this as the last example and go back one more time to my slides. I close this and stop share, screen sharing, share screen, and I go to my slides and share. There we are. And so here, the point that I just already alluded to, which is using this tool allows a teacher to include an authentic lab experience into the curriculum in a virtual lab sense. Because authentic means they're imperfect data, and if you think about it, imperfect data aren't really a nuisance. They're desirable because that's what prepares students to deal with real-world problems, as opposed to solve textbook problems, following some recipe, and everything is always sort of highly mechanical. In the real world, you have imperfect data, and it's perfect for developing scientific reasoning skills. This slide here you just saw earlier, this is mirrors an actual research tool. And my last slide here is, last but not least, it's all visual. In this workshop, that was the theme, molecular visualization. So, good method to reach some majors and weaker students. I'm at 8 morning my time. I will shut down, and thank you for listening. And you can we will all be happy to answer questions. But I will now shut down.
Hello. Hello, everybody. Dr. Jurgen is there on the line. If anybody wants to ask a question, so I'm going to unmute everybody now. So then you can ask your questions one by one. Okay?
Press all to unmute.
All the participants are unmuted. Please ask the questions one by one. Dr. Jurgen, can you please continue to share your screen?
Okay.
Yeah.
I will.
Yeah, Mr. Amit Kumar, you can ask your question, sir.
Hello?
Yeah, Dr. Amit?
Hello. Yeah.
Dr. Amit?
May I ask my question?
Hello?
Hello. Hello. Dr. Amit?
Yes, sir.
So you can please ask your question to Dr. Jurgen.
All right. I'm just asking, sir. Sir, I would like to know PDB file corresponding to any other biomolecule can be obtained in this ODYSSEY software, can be worked with.
Can we do what? Can we? there are builders for polypeptides and polynucleotides. So, and you can, with the entry-level builder and advanced builder, you can, build any molecule sort of atom by atom that you wish. So, in terms of biopolymers, polypeptides and polynucleotides are supported.
प्रिया
So it means we'll have
बज रहे हैं
to.
वहाँ पे सुबह के 5
Yeah.
Are there any other queries? Any other query from anybody?
I'm not sure this format works very well. I think we have to.
Dr. Reena ma'am, can you please wind up the meeting?
Sure. Can you hear me? Can you hear me?
Yes.
Yeah, sure.
Yes.
Okay, good morning, Professor Jurgen.
Yes.
And good evening, everybody. I would like to thank Dr. Shyam Kishore, Professor Jurgen for this talk. It's really a tough time for all of us. We are working from home, staying logged, keeping ourselves logged inside the home. So it was really a delight to hear from you people and learn how to play with the molecules as such on our keyboard and with the help of our computers. I would also like to thank all the participants for sparing their time and being with us for this 1.5 hours long session. And your e-certificates will be posted to you maybe by tomorrow, along with the video recording of the session. Dr. Shyam Kishore and Professor Jurgen have recorded this session, so they are going to post the video recording to all of you along with your e-certificates. Thank you so much. And now I would like to request our principal, Dr. Anjal Srivastava, to kindly give the closing remarks. Dr. Srivastava.
Yeah, Dr. Reena, thank you very much. At the outset, may I welcome Dr. Jurgen to this community of chemistry faculty in Delhi University. We are a big group of almost 20 people in every college, 200 or maybe 200 teachers, and hearing you through the technology of Zoom is again another variation in our normal interaction, and the very thought of doing this academic talk and a workshop in these hard and very stressful times has definitely gotten a little, stress for all of us. And I think each one of us whole talk made sort of get interested in the in variations and that we can do in the students. So it's very promising, and I hope to see more such interactions. I would also like to thank Dr. Shyam Kishore, Dr. Reena, Dr. Bella, and to organize this easy, bring everybody on one platform, and that too through the e-mode. So thanks once again, and I hope you have enjoyed. Once again, really making very happy for being a part of this workshop. Thank you.
Good evening, sir. How are you?
Hello. So thank you all. Thank you all for being with us. Thank you so much.
Yeah, thank you, ma'am.
But for the next series, maybe in the next series, maybe next week or something, if Dr. Shyam and Dr. Jurgen is okay with that.
Oh, sure. And we are also thanking and Yapinder for sharing all that software with everyone. Thank you so much.
Thank you, sir. Now we should close the meeting now. Thank you.
Okay. Thank you so much. Thank you all.
Thank you, madam. Thanks for the participation. Thank you, Dr. Jurgen.
Thank you.